Jai Hind, welcome to the course Network Analysis and Synthesis, and we are discussing network synthesis of this course. So far we have discussed what is network synthesis, and then what are the elements of realizability. We can say that what are the tools required to synthesize a network. Then we also discussed what are the methods required to decompose a network function. So we have used removal of pole at infinity, removal of pole at origin, removal of conjugate imaginary poles, and removal of constant. So either using this or their combination we can decompose a given network function. Then we also discussed synthesis of two elements LC and RL, driving point immitance function using Foster first and Foster first second and Cauer first and Cauer second forms. The one that is the topic left is synthesis of RC network using the Foster first, Foster second, Cauer first and Cauer second. So today we are going to cover this. This is the last topic, synthesis of RC, and then we do carry out some numericals related to the synthesis. So look at the properties of RC impedance, or you can say the RL admittance. Property is same for the RC impedance as well as RL admittance. So all the poles and zeros are simple and located on negative real axis. Poles and zeros alternate on negative real axis. So I am just drawing once again. This is your S plane. This is your G omega axis, this is your sigma. Basically this is the real S and this is the imaginary S. And then poles and zeros lie on the negative real axis on this side, and they alternate. The singularity nearest to origin is a pole. So here we can have pole here, then 0, then pole, then 0, then pole, then 0, and so on. So singularity nearest to origin is a pole, and singularity nearest to infinity is a 0. The residuals of poles of this RC impedance or RL admittance are real and positive. The slope of this is negative, and ZRC at S is equal to infinity is greater than, at S is equal to 0 is greater than ZRC at infinity or YRL. So these are the properties required to check whether the given function is ZRC or YRL. So we know that to obtain the Foster forms we apply the partial fraction expansion. So technique used in the Foster forms are the partial fraction expansion. Okay. So the first Foster form RC impedance is obtained by partial fraction of ZRC. So if the function is impedance we go for the Foster first, if the function is admittance we go for the Foster second. So if the function be satisfying the property of RC impedance, it can be expanded. So this is the partial fraction expansion of a ZRC impedance function. This term is related to removal of a pole at origin, and this K infinity is related to removal of a constant, and this terms how many poles lie on the negative real axis. So this term will come whether in the given function how many poles are on the negative real axis. So where K0 Ki can be at the residuals of the pole at the origin at sigma I and I is equal to infinity respectively. All these constants are real and positive. This is we can look at the property number 5. Okay, if there is no pole at origin, then K0 is 0, and if there is a 0 at infinity, K infinity is 0. So we must remove minimum real part of Zj omega in the partial fraction expansion. That is minimum Zj omega is equal to Z infinity as a register in the partial fraction expansion. When we do this exercise, when the numerator and denominator degree is equal, same, and without disturbing the PRF property. Suppose we divide the numerator by the denominator and we are getting some negative terms in the remainder, then we cannot remove, because the condition is we can divide, we can remove without disturbing the PRF, positive real function property. Okay. So in case when the numerator is of lower degree than the denominator, so this term is 0, means if the numerator is of lower degree, it means 0 is at infinity. When the numerator and denominator of the same degree, then we can obtain Z infinity by dividing the numerator by the denominator polynomials, keeping PRF property intact. Okay, so we can recall that numerator cannot be of higher degree than the denominator for RC impedance function. Okay. So for ZRC, the degree of the numerator polynomial cannot be higher than the degree of the denominator polynomial. Okay. Now come to the Foster first. So if the given function is impedance, then we go for the Foster first, and this is the general expression of the partial fraction expansion. And this term will come when there is a pole at origin, and when we remove a constant we get the R infinity, and this R parallel combination of R1C1 and R2C2 will come how many poles are lie on the negative real axis. So if there are, suppose there are 2 poles, then we will get the 2 R1C1 and R2C2 component, and we can get the values of this R1C1 from this. How will do? We can just I have explained earlier, I can do here also. Suppose this is your R and this is your 1 by SC, okay, and you have to find the Z. So Zs is equal to R into 1 by SC divided by R plus 1 by SC. Okay. So this is R by SC into SC upon SRC plus 1. So this cancel out, then we have R divided by, take the RC, so it will be S plus 1 by RC. So RR cancel out. So we can see that this Zs is 1 by C S plus 1 by RC. So look at this K1 by S plus sigma 1. So what is K1? K1 is 1 by C1. So see what is C1? C1 is 1 by K1. So we can get this term. So if you are not able to remember, then you can find out, okay, hardly matters. Then C2 is 1 by K2 and 1 by RC, 1 by RC is sigma 1. So we can get the R1, which is K1 by C1, this one and this one. So this way we can find the values of these components, and this is the general structure of Foster form of RC impedance function. Similarly, if the given function is admittance, we go for the Foster second, and same way we can find the value of this one and this one we can get. Very simple. What we have to do? We have to just write this, okay, Very simple. R, this is 1 by SC converted into S domain, then ZS is R plus 1 by SC, and then YS is 1 by ZS 1 by R plus 1 by SC. So, this way we can carry out. So, you can simplify this. So, 1 by SCR plus 1 by SC. So, this way we can find the R1 C1, R2 C2, R1 C3, and this is the general expression of Cauer first and Cauer second. Now, do some problems. Suppose this is the given function and you are required to synthesize in Foster and Cauer forms of RC networks. Okay. So, first we have to check, okay, the given function is, because it is Fs, whether it is impedance or admittance, first you have to check it. So, Fs is equal to this. So, we have carried out the partial fraction expansion, okay, and we can plot here, we can plot the, this is S plane, this is your real S, this is your imaginary S, okay. So, we have the pole at the origin, pole at the origin, then we have zeros at -1, then pole at -2, then 0 at -3. So, poles and zeros are simple and lie on the negative real axis, okay, first, and they alternate. We have the, at the origin we have the pole, then we have the 0, pole, 0 and so on. The singularity nearest to origin or at origin is a pole. Singularity nearest to origin is a pole and singularity nearest to infinity is a 0, okay. And the residuals are, poles residuals are real and positive, 3 and 1. Then we can also check for the f0 and f infinity for this function. So, here in this case the f0 at s is equal to 0, when limit s tends to 0 is greater than when the limit s tends to s infinity. So, f0 is greater than f infinity. So, the given function is ZRC, or you can say the YRL. Property are for the both ZRC and YRL is same. So, the given function is ZRC. So, we go for the Foster first. This is the, once we have got decided the given function is impedance, then carry out the partial fraction expansion. Here the degree is same, we can say the numerator and denominator degree are same. So, we just divide the numerator by the denominator to remove, this is Z infinity getting as a R infinity, clear. And then then we have the pole at origin, s is equal to 0. So, we are getting this term, clear. Then we have a pole on the negative real axis, here we have this pole. So, we are getting this term. So, there are 3 terms corresponding to pole at origin, removal of a constant, and pole on the negative real axis. So, we have the 3 terms. So, this and this, okay. So we can find the value of k0 and k1 using this partial fraction expansion, and then we can fabricate or just get the Foster first form. So this is basically this is R. This is your pole at origin. This is your C0 and this is your C1 and this is R1. So very simple, just identify the given function whether it is ZRC or ZRL or YRC or YRL, then carry out the partial fraction expansion. Before carrying out the partial fraction expansion, check whether the given function is proper rational or not. If not, then just divide by the numerator by the denominator to get the proper rational function, and then partial fraction, find the constant, and we can get this. Foster second. So the given function is your ZRC or YRL. So if I considering as a YRL, okay, then we go for the Foster second. For the admittance function we go for the Foster second, for the impedance we go for the. So just invert the function, given function is ZRC, invert it and carry out the partial fraction expansion, we can get this. So this is the Foster second of YRC. So if you remember, property of YRC, RC admittance or RL impedance were same. So in that case, for YRC, the poles are residuals of poles are real and negative. So what we do, we just divide by S. Remember, if you divide by S to make the coefficients real and positive. So this function, in this case the K1 and the poles residuals are real and negative. So divide by S, and then we can find the K1 dash and K2 dash, and this way we can fabricate. So these are the values of R1, C1, R2 and C2. Here we can see here there are two poles on the negative real axis. So there will be the two R1, C1 in series component of R1, C1 connected in parallel. For the chord first, function is given, arrange the functions in the descending order and divide the numerator by the denominator. The technique behind chord first is carry out the continued fraction expansion about pole at infinity. Okay, so just arrange the polynomials in the descending order and divide. Simple division. So carry out, if it is impedance, starting with the impedance, then first term will be the impedance, then we have the inverted. So this is the admittance, then impedance and then admittance, and we carry out the continued fraction expansion until we get the remainder 0. So these are the, now we can write here. So this is Z1 is 2, so it is 2 ohm. Then Y2, it is admittance, so it is 1 by SC, na Z is 1 by SC. So YS is equal to SC. So this is your C, this is S, and so on. So these are the chord first. So in chord first you have to carry out the continued fraction expansion about pole at infinity. for that we have to arrange the polynomials in descending order and divide the numerator by the denominator. In cosecant we carry out the continued fraction expansion about pole at origin. So, for this what we do, we just arrange the polynomials in ascending order and then we divide the numerator by the denominator polynomials and we can get. So, starting with this is Zs, so this is Z1, first term will be Z1, then we have the inverter, so Y2, Z3 and Y4. So, these are the capacitor, then resistor 2 by 5 admittance, so for impedance it is 5 by 2, 1 by 25 and 10. So, this way we can carry out the synthesis of RC network in Foster first, Foster second, Cauer first and Cauer second. Suppose this is the typical numerical synthesize the given function in Foster forms, whose admittance function is given by Ys is equal to s plus 4, s plus 6, s plus 3, s by plus 2. The first and foremost we have to check whether the given Ys is Z, YRC or YRL, first and foremost. So, what we do, just draw here. This is your real S, this is your S plane. Never forget to mention S plane, this is your imaginary S. So, first S is equal to minus, so there are two poles, so poles at S is equal to minus 3, then we have 0 at minus 4, then we have pole at minus 5, then we have 0 at minus 6. Okay. So, this is the simple pole 0 diagram of given network function. So, we can see that poles and zeros are simple and lie on the negative real axis and they alternate. The singularity nearest to origin is a pole and singularity nearest to infinity is a 0. And if we carry out the partial fraction expansion, we can get the poles residuals are real and positive. If we carry out the partial, just divide this and find the value of K1 and K2, they are coming real and positive. So, just I am doing here Ys is equal to, we can write s square plus 10s plus 24 s square plus 8s plus 15. Take one division, it is coming, then it is coming 2s, divide 2s upon 2s plus 9 by s plus 3 and s plus 5. So, Ys is equal to 1 plus, now this is the proper rational function. So, carry out the partial fraction, say this is your K1 by s plus 3 and this is K2 by s plus 5. So, we can find the value of K1 and K2. So, K1 is equal to, this is s plus 3 into 2s plus 9 s plus 3 s plus 5, put s is equal to minus 3. Okay. So, this is the Heaviside expansion theorem where you can remember how to get the value of K1 and K2. So put k s is equal to minus 3, so it is coming minus 6 plus 9, so it is 3 and by 2. 5 minus 3, it is 3 by 2. Similarly, we can get the value of k2. So it is s plus 5, 2s plus 9 divided by s plus 3 and s plus 5, s is equal to minus 5. This cancel out. So this is 2s minus 10 plus 9, this is minus 1, and minus 5 plus 3, so minus 2. So k1 k2. So what we are concluding, poles and zeros are simple and lie on the negative real axis. Understood here. The singularity nearest to origin is a pole, right? Singularity nearest to infinity is a 0. You can see here tending towards negative. Okay. Residuals of poles. Poles residuals are real and positive. Okay. At the same time, we can also find out what is your ZRC 0, because it is admittance, so we go for the Y, not ZRC and ZRL and YRC, YRL. We don't know what is the given function. So what is Y0? So Y0 is basically put s is equal to 0, so 64 divided by 50. So 6 into 4, 24 divided by 50. So it is 8 by 5. I think 8 by 5. And similarly, we can find the y infinity. So how will get the, just carry out the s 1 plus 4 by s, then s into 1 plus 6 by s divided by s into 1 plus 3 by s and s into 1 plus 5 by s. So this s cancel out and limit. Now put limit s tends to infinity. So this is 0, 0, 0. So y infinity is 1. So we can see here y0 is greater than y infinity. So from the given function we have concluded these 4 points, and on the basis of these 4 points we can conclude the given function is YRL. So the given function is, so here we can write given function is YRL, okay, or ZRC. ZRC we cannot write because it is admittance function, okay. Property are same for the ZRC and YRL, but the given function is admittance, so we consider at a YRL. So once we have find out the YRL, then we can, so YRL, so 1 plus it is 3 by 2 s plus 3, then 1 by 2 s plus 5. Okay. So here we have a constant, then 2 poles on the negative real axis. So we can find the structure. Structure will be like this. This is admittance, so it is conductance. Then we have so this is R1 L1, this is R2 L2, and this is R infinity, so it is 1 we can write the mho or ohm. Now we have to find the, basically it is R infinity. Now we can find the value of this R1 and L1. How we will do? Just remember this. This is your R, this is your SL in S domain. So ZS is equal to R plus SL. So YS is equal to, because it is the admittance, so 1 by R plus SL. So take the common 1 by L S plus R by L. Okay. So this is, we can write here 1 by L S plus R by L. So 1 by L is 1 by L is 3 by 2. So L is equal to 2 by 3 Henry. Similarly, R by L, this, look at this one, S plus 3. So R by L is equal to 3. So R is equal to 3L. So R is equal to 3 into 2 by 3. So it is 2 ohm. So it is coming 2 ohm and 2 by 3 Henry. Similarly, we can carry out for this. So this one is, so 1 by L is equal to 1 by 2. So L2 is equal to 2 Henry. So it is 2 Henry and 2. So it is 5 L. So L is 2. So it is 10. 5. Here from this expression we can get this 10 ohm. Okay. So this is the YRL. Okay. YRL we can find using the your properties, and this property is also for the ZRC. So suppose in the question admittance function is given and you are required to find the RC Foster form of RC network. Try to listen carefully. Admittance function is given, okay, and you are required to, because in this particular problem it is nothing, it has not mentioned whether we go for the RL or RC, but in the questions if it is required to just synthesize the given function in RC Foster form. So what we do, just I can write a straight way. I can write a straight way. How I just look at this is your Foster second. This is Foster second of RL network Okay. If it is required to go for the Foster first, then just invert the function, make it impedance, and then carry out the partial fraction expansion and fabricate. Now straight away I can write here Foster first of RC. Straight away I can write. So this is 1 ohm, this will be half ohm, this will be 2/3 farad, this is 1/10 ohm, and this is 2f. Okay. If you go for the partial fraction expansion, considering at ZRC and try to find the value of the K1 and K2, we can get this. But you should be smart and intelligent. What I have done here, I have just applied the dual property, duality I have used here. Look at, this is the admittance. So the dual of the admittance is impedance. Okay. This is all the components are in parallel. All the components in in the Foster second of the RL network are in parallel. So dual will be, all components will be in series. This is this and this, all will be in the series in the dual network. Remember, okay? Look at here. This is your impedance, okay? So dual of impedance is admittance, okay. So what we do in the dual, we take the magnitude as it is, just we change the unit. So 1 ohm or 1 mho, same. So it may be 1 mho, we can write the 1 we can write, the 1 mho. So 1 ohm and 1 mho, same. Then this R1 and L1, they are in series, okay. So in the parallel, in the dual network, they will be in the parallel. So R1 is Y1 and L1 is C1. So Y1, so 1/, so Y1 is, this is the I1, so magnitude will be same. So it will be 2 mho. We take the magnitude as it is, we just only change the unit in the dual network, remember. So this is the 2 mho, 2 ohm, 2 mho, or we can write the half ohm. Here 2/3 Henry, here it will be 2/3 farad. Come to this is 10 ohm. So in the dual network, the R2, L2, they are in series. So in the dual network, they will be in the parallel. So they are in parallel. So 10 ohm will be 10 mho. 10 ohm in dual network, it will be 10 mho. So 10 mho, or we can say the 1/10 ohm. So we can write here 10 mho. 10 ohm. And this is the twice 2 Henry. So in the dual network, it is 12. So we can just if you are intelligent, you are smart, you can apply the dual property, but don't do this. We just for checking point of view we use here. So we can carry out. We just carry out one more problem. So this In 1978, it has been asked in the engineering services, and the problem is like this. I am just realize the function in the Cauer first and second forms RC network with pole 0 diagram is given below. So, just I am drawing here the pole 0 diagram. This is your S plane, this is your real S, this is your imaginary S, and we have pole at origin, then we have 0 at -2, then -3, and then we have the 5. So, this much is given, okay, S plane and pole 0 diagram. And one more thing is a scale factor is also given. In some numericals we have to find a scale factor also, but in this particular numerical scale factor is given here. And what is a scale factor? Just I am explaining. If you remember, network function generalized form, it is Bm s to the power m Bm minus 1 s to the power m minus 1 plus say B1 s plus B0 divided by An s to the power n plus An minus 1 s to the power n minus 1 plus A1s plus A0. Okay. So, this is the general form. This is the general form of a network function. General form, or you can in the form of the polynomials. Suppose say this is ns by ds. Okay. Put ns is equal to 0. The numerator polynomial in S, put equal to 0, it becomes equation, and we can get the m roots. We get m roots. Say Z1, Z2, Zm. Put ds is equal to 0. If you equate polynomials equal to 0, it becomes equations, and we get roots. How many roots? N roots. Say P1, P2, Pn. So, this above function can be written as S minus Z1, S minus Z2, S minus Zm divided by S minus P1, S minus P2, S minus Pn. So, this H0 is nothing but it is the ratio of Bm upon An, and it is known as a scale factor. Okay. So, from the pole 0 diagram we can write Fs. So, on the next, so Fs is first H0 is 2, zeros at S is equal to -2, -5, poles at S is equal to 0, -3. So, now from the pole 0 diagram we can find the function. So, here H0 is 2, it is given in the numerical examination problems. Then we can write here. So, S plus 2 s plus 5 s into s plus 3. Okay. Now just you have get the network function, then you can find the from the property whether it is ZRL or YRL or ZRC or YRC. Okay, and then we can proceed. So, just the given function is ZRC, so it is ZRC or YRL. So for now we can proceed. So I'm no need to just find the solution. You can just my idea is just to explain whether the pole zero diagram is given and how we get the network function. Once we get the network function, then check from the property whether it is RL or RC, which type of RL and RC, impedance or admittance, and accordingly proceed. So this is the last topic of synthesis, RC. So far we have discussed, if we summarize, then we discussed the network synthesis, that is the design and fabrication of a network when the input and output are known. Then we also discussed the what are the tools to carry out the network analysis. It means before carrying out the your network synthesis, the function must be a PRF. Then we also discuss what are the methods. Very important. This is the soul of the your network synthesis. Methods of network synthesis. So there are 4: removal of pole at origin, removal of pole at infinity, removal of conjugate imaginary poles, and removal of a constant. So all these 4 methods we use. Then we carry out the synthesis of RC, RL, LC network. 2 element. Okay. One thing I am just want to tell you, for the LC, if you remember the property, it was ZLC or YLC. So if it Fs is given, Fs is given, it can be impedance, it can be admittance. Okay, because in the property, if you remember, ZLC and YLC are the ratio of even to odd or to even polynomials. Okay, we cannot distinguish whether the given Fs is impedance and admittance. We can take as a impedance or admittance for the same function, whereas for the RC and RL we have the we can easily differentiate on the basis of the properties. So this is all about your network synthesis. Thank you very much. From the next class I will take another unit, probably it will be the transient circuit analysis. So thank you very much. Jai Hind.